recording here is that I would just kind of quiz you guys over some things. Okay. So the point of the lecture on all of that was covering a little bit about how we assess muscular strength, right, and local muscular endurance, and then kind of how we prescribe exercise or resistance training and those types of things. Okay. So let me just see how we're doing on all of this. I'll just randomly sort of pick someone. Chandler, are you there?
Yes, I'm here.
Chandler, what's a 1 repetition maximum?
It's an exercise you can perform once with good form.
Once with good form. Very good. Okay. So one of the ways that we measure muscular strength is to do something called a 1 RM or a 1 rep max. And in theory, we can do this for any type of weightlifting exercise that we have. And a 1 rep max represents the most weight you can lift one time. You do it once, you try to do it a second time, you cannot do it, okay? It's only once. And typically those are during what we call dynamic muscular contractions, things like a squat or a bench press or a bicep curl or a shoulder press or something, okay? 1 rep max, most weight that you can possibly lift. Emma has a question. We'll go to Emma and then we'll go to Nia. Okay, Emma, what's your question?
So I remember in the lecture you were talking about how like it would be ideal if people are like working on trying to create their workout programs and stuff, if they determined their 1 rep max for all the different like exercises they wanted to do and then used that as like, I'm going to do 80%, however many reps and all that fun jazz. So how would you do that if you wanted to just like figure out what your 1 rep max is on like a leg press or something? How would you do that in just like casually, or can you do that casually?
I don't, casually, I don't really know what you mean by casually, but like you can, what I would say is you just go to the gym and you want a leg press, you throw as much weight as you think you can lift on the leg press and you try to do it once. And if you can get it, then you like wait 5 minutes and you put a little bit more weight on there and do it and try it again. And then if you don't get it, then you can take a little bit of weight off, kind of somewhere in between, and you just try to kind of go up and down. There are specific instructions on how to do it that are in the lab. That's one of the things that we do in lab. If you're really curious, it's in the lab instructions. But I mean, you just go and do whatever lift you want to do and just start grabbing weight. And the really key thing is form and rest time. You want to make sure that you rest sufficiently in between attempts, because if you don't, as we will see when we get into talking about fatigue and some of our kind of cardiorespiratory things, that you do it once and it costs you some energy and things, and it costs you some creatine phosphate, and you need a little bit of time for all of that to recover. So usually we tell people you need to wait like 3 to 5 minutes in between attempts. So that's how you would do it. And so Emma kind of stole what my next little piece of things were going to be. Nia, I know you had a question, so we'll do your question, and then I'll talk about why what Emma had asked about is maybe one of the most key things from all of the entire lecture from Friday.
I had like the same question as her.
Oh, just like how do you do it? Okay.
Yeah.
Okay. So the reason that knowing your 1 rep max is so unbelievably important, okay, is that if you're going to go and do resistance training, and I hope that many of you pointed this out in your resistance training critiques that you turned in yesterday, because very few programs that you find anywhere suggest that you do this. The most correct, which is a terrible sentence, but the most ideal and correct way to adequately prescribe intensity for resistance training, okay? We'll talk about the FIT principle and we'll talk about overload here in just a second really quickly, but the most accurate way to prescribe intensity, to make sure that it's enough, we need to know your 1 rep max, okay? So for most people, that should be the first thing that we do. You're going to start doing resistance training. We need to find your 1 rep max at all of the lifts that you're doing. Once we know that, then we can say, and there are tables and things if people care. You would say, like, I need to do 3 sets of 8 repetitions. If I know my 1 rep max, if you're doing 8 repetitions, you ought to be able on most lifts to do about 80% of your 1 rep max 8 times. And if you're doing 5 or 6 reps, it's probably about 85%. And 3 or 4 reps is about 90% or thereabouts. If you're doing 10 reps, it's about 70 to 75, depending upon kind of how complex the lift is going to be. Okay? So we need to know 1 rep max because it lets us individualize the amount of weight that everybody needs when they do resistance training. Okay? And so you guys probably noted, hopefully if you saw it, that there are recommendations on most people need to lift between, say, 60 and 80% of their 1 rep max for somewhere between 8 to 12 repetitions, several times per week for a couple of sets across multiple exercises in order to kind of get this whole body resistance training benefit. And so if you're doing less than that because you don't know what your 1 rep max is, then that can be a problem and you're not going to see all of the positive adaptations that we're going to get. So when I joke around and I say things like, I tried to get a picture of my daughter this weekend. We were at her great aunt's house and her great aunt had 1 pound dumbbells. 1 pound dumbbells. And my daughter was running around with these 1 pound dumbbells. And I was trying to get a picture of her to like put in the PowerPoints to say that, you know, if my daughter can carry around 1 pound dumbbells and throw them around like nobody's business, there's no reason that any adult should ever be lifting a 5 pound dumbbell and doing things. And the problem is that you lift a 5 pound dumbbell and you're like, oh, I'm going to do some curls and some overhead press with these 5 pound dumbbells, which I'm sure none of you all have ever done that. But if we went over to the Huff, we'd probably see some people that were doing this. Then you're at, you know, if like with a curl, many of you can probably do, I don't know, ladies, 20, 25, 30 pounds, guys, probably 35, 40, 50, 80 pounds, who knows, depending upon, you know, how many curls, guys, that you do. And so 5 pounds is, if your max is 20, 5 pounds is like 25% of your 1 rep max. It's nowhere near enough intensity to ever actually make you change your recruitment patterns or to evoke things that are going to cause muscle hypertrophy. Okay, that's why we have to know 1 rep max. That's the importance. Okay, now for a lot of people, the other way to do that, though, it's not always safe to do a 1 rep max in everyone. And another alternative is to do what we call a multiple repetition max. And so that would be like, I know that I want to do sets of 8 repetitions or something. I can find the most weight that I can lift 8 times, but not 9, right? Or I can do it 5 times, but not 6. That's called a multiple repetition max. And if you know your multiple repetition max, you can estimate your 1 rep max based upon that. There's some tables for that. Or if you know what that is, then you're going to say, I'm going to do 3 reps of 8 repetitions with my 8 rep max, or with 90% of my 8 rep max, something very, very close. That way you know that you're going to be able to do about 8 reps, but not a 9th each time, or very, very close to all of that. Okay. So those are kind of the things, but the key take home is we need something, okay, that allows us to estimate or get close to estimating your maximal strength so that we can accurately prescribe intensity. Okay. Okay. Let me see. We'll pick someone else. Caleb, are you there?
Yes.
Okay. Caleb, do you remember what an MVC is? Do you remember looking at anything about a maximal voluntary contraction? and why that might be different than a 1 repetition max.
An MVC.
Mhm.
I don't remember seeing anything like that.
Okay, that's all right. Does anybody else? Anybody help Caleb? No? Okay. So what we would normally do in lab is we do a grip strength test, okay? And so you get this thing and you squeeze it. Ooh, wait, I actually have one in here in my office. I take said thing and I squeeze it as hard as I can. Okay, I squeezed a grand total of 28 kilograms. That's pretty weak sauce. Okay, based upon the things in the deal, I'm probably going to die in about a week based upon what that number was. Okay, but that contraction, nothing moved. Okay, that's an isometric contraction. And so when you do a maximal isometric contraction, that's called a maximal voluntary contraction, or an MVC. Okay, so depending upon what it is that you're doing, you could also get an MVC on a person and use that as your kind of maximal top end strength thing and do some prescription based upon that. Although we don't do a lot of things where we do just isometric contractions. Okay, typically isometric contractions are used in research. They're a little bit more like reliable, and they're a better indication of muscle size and muscle mass and some of those things. Okay. Okay. Let me pick somebody else. Madison.
Yes.
Do you remember seeing something called the FIT principle?
Yes.
Do you remember what the F in the FIT principle was?
The F's for frequency.
Good. Okay. F is for frequency. Very good. Let me pick somebody else. Sunny, are you there?
I'm here.
Do you remember what the I in the FIT principle stands for?
Isn't it interval? Or no. Intensity.
Intensity. Very good.
Right?
So we have frequency,
Okay.
intensity, good. And then we've got 2 T's. Blake, do you remember what either one of the T's are?
Hey, yeah, I'm here. Time and type.
Time and type. Very good. Okay. So the FIT principle provides us with a framework, okay? A framework to either analyze a program or to come up with our own exercise thing. We want frequency, which is the number of days per week that we're going to do something. We want the intensity, which for resistance training is some percentage of 1 rep max, okay? Time, for resistance training, time is not necessarily going to be in minutes. Time is like the number of sets, the number of repetitions that we're doing. And then type is it leg press? Is it bench press? Is it free weights? Is it a machine or something like all of that? And so if we know all of those things, I'm going to do 2 days per week at an intensity of 70% of 1 rep max. I'm going to do 2 sets of 10 repetitions on squats and bench press and shoulder press and like calf raises or something, okay? We're going to do a straight like total bro workout. So it'll be bench press, incline bench press, decline bench press, cable flies, because they love nothing better than to occupy all the machines doing things that don't really matter, and then some calf raises. They're not going to squat, they'll just do calf raises because bros love their calves. Okay, so that's how we apply the FIT principle. All right, does that make sense? You guys understand kind of how that goes? And so hopefully with your resistance training critique, you looked at what your program was asking and said, okay, its frequency was this, its intensity was this. And maybe some programs don't put that in there. Some of them are just like, I saw some of the ones y'all sent me and it was like, okay, like do 10 reps, but you're like 10 reps with how much weight? Then they're never set, okay? And so you can kind of do all of those things out in that way, and it provides this nice little framework, okay? The thing, and I see you, Nia, but the thing where people mess up the most, okay, and this will lead us into the next little piece that I want you guys to take home, is they mess up on the intensity part. People don't work at a high enough intensity, right? I go to the gym and I go lift 4 days per week, and that's great. And maybe I'm doing a sufficient number of sets and reps, and I'm doing the right exercises. But what oftentimes happens is people don't do enough intensity, okay? They don't do enough intensity. And so that's kind of where our problem is going to be. Ideally, I see you as well, Sydney. Ideally, you want your intensity to be 60 to 80% of your maximal strength or above. An alternative way to think about this is when you're doing an exercise, okay, if you are wanting to do, say, a couple of sets of 8 repetitions, for both of those sets, for sure for the last set, you want to be able to do 8 repetitions, but maybe not a 9th, okay? We want to work to something that we call failure. And if I got 8, I'm going to try 9. If I got 9, I'm going to try 10. I'm going to go to the point to where I cannot physically do another repetition. And if I get like 2 more reps than I was aiming for, then it's time to add 5% in weight or something like that, okay? The idea of working to failure and the idea of using these kind of relatively high percentages of your 1 rep max helps us push the muscles beyond the point that they're normally used to doing. And this gets into the PROS parts of our principles. It gets into something called overload. We have to work the muscle harder than it normally works. We have to overload it in order to stimulate it to get bigger and to stimulate the nervous system to try to alter the way that we recruit motor neurons and things so that you can get stronger, okay? And that's where people miss most often. They don't lift to failure, or they don't lift heavy enough, and therefore they're not going to get as large of adaptations as what they're hoping for, okay? Nia and then Sydney on questions. Nia.
So I have like 2 questions.
Okay.
So with the intensity part, I know you said like a lot of programs don't really like specify that, but I'm trying to, okay. So for example, if it was just a dumbbell workout, but they don't specify how much weight, but they say like, you know, they do this many reps and like this many sets, couldn't it be more like for a person that has less fitness history, couldn't it be a more vigorous activity rather than somebody that's doing the program that's more physically inclined, like, you know?
Okay, so you ask a really great question, Nia. It's really great, okay? So one of the other things that we were going to talk about with progression and overload, the wonderful thing about using maximal strength to prescribe your intensity is that it lets us individualize things to everyone based upon where they are from a strength perspective, which is solely based upon their exercise history, right? People that have worked out more previously tend to be better and stronger at certain exercises. So when we use a percentage of maximal strength or something like that, what it does is you do a lot more things than I do, so then 80% of your maximal strength is going to be more weight than 80% of my maximal strength, yet we are both going to kind of overload and give ourselves a similar kind of relative overload or relative kind of stimulus, which should help drive adaptations. But I'm doing a lot less weight than you're doing, or maybe I'm doing fewer repetitions than you're doing because we're working all the way to failure or something. But in theory, then it makes the workout kind of intensity similar between us, even though we're doing very different weights, if that makes sense. And so like what I would tell you guys is, so like yesterday, when I went to Orange Theory, we don't do anything where you use a whole lot of weight. You do a bunch of exercises, and I need to email their scientific advisors. Their head science research person is a UGA grad. I don't personally know her, but I know of her. And some of the things that they do they're not great. But I was doing curls at the very end, trying to do 15 reps with 8-pound dumbbells, because we were doing stuff where it was we were doing rows, and we'd done multiple sets of rows and other things that use your biceps, and then some curls. And by the end, I'm I can't lift anymore. And so I was dropping my weight so that I could get to failure at about the prescribed number of repetitions. And in theory, there is some evidence that is just as useful as if I was doing, a very bro-ish 3 sets with absolutely as much weight as I could possibly lift, that I maybe can get the same kind of adaptations from that. So there's some gray area and some nuance and art that goes into prescribing things in this way. But whenever possible, if we can get a maximal strength measure and use that as our benchmark for prescription, that's the best way to do it. Okay. Okay. Sydney.
I have read and taken a lot of ACSM courses, and my question to you is, do you think it's more difficult to get a true 1 rep max for a beginner, since they probably don't know how to work to failure?
Absolutely.
Do you have any workarounds for that, or just deal with it?
So, and this again is the wonderful part of us doing, we actually get to do the lab in person, and I apologize that you guys are getting short shrift on this, but one of the reasons that I pick bench press is because the class is usually 75 or 80% women, and of that 75 to 80% of women, women are much less prone to doing bench press than men. Although we usually have people that have done it some, but we usually have half of the girls in class have never done one. And that's very useful from a teaching perspective, because what happens is they don't know what they're doing. And so we're going to get a 1 rep max on that day with the beginner who's never done something. And then if we had them come back the next day or the day after and do it again, they're going to get neural adaptations immediately and be immediately stronger, right, within a couple of days. So probably the best workaround you can just get it and then give them something and then test them, have them do stuff for a couple of weeks and then assess them again and rejigger things. The other suggestion that I have seen that people will do is just teach them technique, right? Give them light weights, spend a couple of weeks working on teaching them how to do the lifts with a very easy weight, kind of ease them into things, give them a little bit of a ramp up. And then once you feel like they've begun to master and understand the technique, then you go ahead and assess their 1 rep max, and you're going to get something that's much closer to what their true maximal strength is. And then you can prescribe based upon that and then kind of continue on. Okay. So this is as good a place as any. And Chandler, I see you, and Julia, I see you, for me to talk very briefly about the concept of progression, okay, which is part of that PROS principle. Overload is you got to do more than what you're used to doing, or you're not going to adapt, okay? Progression is the idea that as you adapt, I've been doing overload, I've been reaching beyond where I normally am. That's going to drive adaptations. I'm going to get stronger, okay? And so as I get stronger, I have to reassess my maximal strength so that I can then redo the amount of weight that I'm lifting. Because if my 1 rep max is now wrong, I'm actually not working at the correct percentage of my 1 rep max. So if my 1 rep max was 100 pounds and I've been doing 70% and I've been lifting 70 pounds, but over the course of a month, my 1 rep max has now gone up to 130 pounds or 140 pounds, now I'm doing 50% of my 1 rep max. And so I need to progress and reassess my maximal strength and up the amount of weight that I'm lifting to get back to that 70% value or something like that, okay? And so there's some laid out guidelines of should you reassess 1 rep max every month or every 6 weeks or every 2 months or something like that. You know, that's kind of a prescriber's choice type of thing, but the key thing is that you need to reassess. But if you do things like what I mentioned earlier, where I'm doing 70% for 12 reps, if you get to where you can do 12 reps and you can do 13 or 14 reps with it, then that's probably a sign that it's time to progress and that you've gotten stronger, and now you need to add some weight to get it back to where you can do your 12 reps or something. Okay, that's probably the best way to kind of prescribe it. That's what progression in there we want with those things, okay? The key thing that drives adaptations to resistance training and aerobic training and flexibility training, everything, is progression and overload, which are sometimes mashed together. It's called progressive overload. And that just means that do more than what you're used to doing. And when that becomes a little bit easier, make it harder again. That's kind of the easiest way for me to do that, to kind of explain that. Lift something, go to failure. When you can do a few more reps before you get to failure, add some more weight on, and you're fine, okay? And you just kind of keep rolling. Okay, Chandler and then Julia.
My program that I chose had a bunch of supersets, and I was just wondering if those are actually beneficial.
It all depends upon how we define beneficial, Chandler. The really kind of most basic answer from me is no. It all depends upon what your goal is also in some ways. Like, what are you trying to get out of doing this? If you're training for a particular sport or, excuse me, something that's going to require something that looks a lot like doing a superset, where you're doing multiple exercises with the same kinds of muscles with very little rest in between, you got to drop weights and those kinds of things, then maybe that's going to more closely approximate whatever it is that you're doing. And so that could be of some benefit. But if you want to maximize your increase in strength and your increase in muscle size, no, there's not really any evidence that that is particularly better than, you know, we make a big fuss over all of this stuff. And most of it is you're really, really, really playing in the margins, right? Like, do the ACSM guidelines, lift somewhere between 6 to 12 repetitions at somewhere between 60 to maybe 85 or 90% of your 1 rep max. Do a couple of 3 sets of an exercise a couple of times per week. Make sure you're getting some protein in your diet. When it gets a little easier, add some more weight. Maybe every 6 weeks or so, change it around from doing sets of 6 to sets of 8. Just keep doing that, and you're going to get 90% of whatever your genetic potential, or 95% of whatever your genetic potential is, simply from doing that. Everything else is hand waving to sell you something most of the time, right? That's my sort of take home on all of that. The key thing is to actually go and to actually do it, right? You know, that's how you get things. There's no magic trick, right? Oh, this is the one thing that's going to make me get really huge. No, just freaking go, right? You know, just go and lift. I will at least give some of that to the bros. At least the bros are going. We can argue about whether they should be bench pressing that much, but they're bench pressing a lot and it's heavy. That's reasonable. That's why they're going to, you know, we're going to get some pecs out of all of that. So anyway, okay, Julia, and then we need to probably move on.
So based on what you were saying, seems like you can increase the intensity of like an exercise in other ways than just going up in weight. So for example, if I'm doing like a bicep curl, I hold one arm isometric and then I curl the other one 8 to 12 reps and then I change. How beneficial is that compared to just going up in weight and doing 8 to 12 reps that way? Or doesn't make a difference? It doesn't. Okay.
You know, it's kind of like doing a superset. It's kind of like all of those things. So I think you guys may remember that I told you that we don't fully understand all of the molecular signals that are going to lead to the increase in muscle mass. They're going to drive hypertrophy. There is a thought, not a huge amount of evidence, but there is a thought that one of them is a metabolic trigger. And so what you need to do is you need to basically, by getting to failure, right, you're taxing not only the muscle and strength, but you're also taxing sort of your anaerobic metabolic systems that are in there. And so, you know, there's some evidence that that is one of the things that may play a role. And so by holding something isometrically, what you're doing is you're sort of pre-fatiguing the muscle by doing all of that. And then it can let you get to failure using fewer reps or a lighter weight or something than what you could do otherwise. Our department chair, Dr. Mike, they're interested in research that's called blood flow restriction, or KATSU. I don't know if you guys have heard of any of that. If you guys had Eduardo or anybody, you know, for personal training or something, what they do is, like with my bicep, they would put a blood pressure cuff on right here, and they inflate the blood pressure cuff, and it cuts off some blood flow to my muscle. So when you cut off the blood flow, then you have me do a bunch of reps with a very light weight, I get fatigued, and they leave the blood pressure cuff inflated. And so I'm still depleting and doing anaerobic metabolism because I can't get any oxygen to my mitochondria. So then when I do another set, I'm lifting like 30% of my max, but I can only do it 8 times. And there's very good, very widely done, many times evidence that working out like that, I can use 25 or 30% of my 1 rep max, and I can get just as much hypertrophy as if I'm lifting, let's say, 80% of my 1 rep max. What you don't get, though, when doing that is you don't get all of the neural adaptations to get as much of an increase in maximal strength. You get better at doing whatever it is that you're doing. And so the nervous system then gets better at doing 8 reps or 12 reps or 30 reps or something. And so if you really care about being as strong as you possibly can, you just need to go lift heavy weights. Like, go practice doing 1 rep maxes. That's how you know, if you're going to be a power lifter and your entire thing is based upon one chance at the most weight you can lift one time, then you need to try to do that a bunch to practice it. And that's how you, that's kind of how you would max that out. So those other kinds of things may get you equal hypertrophy, but it's not going to get you equal increases in strength. But there's maybe some usefulness, like in older people or people that are rehabbing an injury or something. They can't lift 80% of their 1 rep max safely, right? Like your post ACL tear or something, and we don't think it's safe for you to do knee extensions or squats or leg press with that much weight. Maybe you could do this alternative and get an equal hypertrophy by using a lighter weight or something. Okay. All right. I really think that I kind of hit the high points of what FIT and PROS is on most of that, but that's going to be something that's going to show up on the test. Like, I could either give you something like a program and have you guys tell me, like, what, using FIT, what are we doing? Is it good or not? Or is it adhering to progression, repetition, overload, and specificity or not? And like, what's going to be the consequences of whatever those particular things are? Okay. Sydney, you have a question? No. Okay.
No, I apologize. My dog is stuck under my couch. So.
Oh no! Rescue her. Okay. Anybody else have questions about some of those kinds of things? Nia, do you have another question, or is this from earlier? You got one?
Yes.
Fire away.
While I was doing my critique, I was a little confused on the specificity part of the pros.
Okay.
Like,
you just want me to talk about what specificity is?
Yes.
Okay. Let me do this. Taylor, are you there? Uh-oh. Okay, I was going to ask Taylor something. That's fine. So the idea behind specificity is that you need to train on, like, if you have a goal of what you're trying to accomplish from training, let's just say, then based upon what that goal is, you need to train in a way that is going to be very specific to getting the adaptations that will help you reach that particular goal. Okay? So if my goal is, let's just say, I was going to pick Taylor. Taylor plays on the basketball team. I was going to say, if Taylor wants to get better at shooting free throws, she needs to practice shooting free throws. She doesn't need to go run suicides or something, or maybe do squats or something like that, right? The adaptation to get better at shooting free throws requires you to shoot free throws. If you want to get stronger, let's just say, at doing things that, like a squat, don't go bench press. You need to squat, right? If you want to get better at squatting very heavy weights, you need to go squat with a very heavy weight, okay? And so usually when you start a program, you might want to lay out like, I want my legs to be stronger, or I want my, I want my quads and my glutes to be stronger specifically, so I need to focus on that kind of stuff. Or I'm working on things that are going to make me jump higher. So those require these muscles across these joints, etc. So you have to train and work the muscles at the proper intensity and things that are going to let you get adaptations to meet whatever your goal is. That's the idea of specificity.
Okay, so just working on like a specific goal that you have.
Right. And a lot of programs will just say things like, we don't have a goal. Or some of y'all, they're like, our goal is we're going to shred your abs and, right, like do all of this. So if it's a shred your abs program, and they're having you do arm stuff, that doesn't seem like it's very specific, right? Although I would argue that if you want to get more visible abs, it might actually be useful to try to make your larger muscle groups bigger, because you'll burn more calories that way. So by doing like squats and leg extensions and those kinds of things, then you'll burn more calories, which might be helpful for at least the appearance of our abdominals, if not necessarily our strength. Because that's the other kind of misnomer, right? Is people, they talk about, we're going to shred your abs. They don't care if their abs are strong. They want them to look a certain way. And that does not mean that they're strong, right? So cross-country runners have very visible muscles, right? We were watching, because I'm a crazy person, we were watching the U.S. Olympic trials this weekend and watching some of like the distance runners. And they're all ripped. I mean, they don't have very big muscles, but they have no subcutaneous body fat. And so you can see every muscle that they have. And for some people, that might be a very desirable characteristic. I want to look like that. Well, they don't do a lot of weights. They just run a bunch and they don't eat anything. So they're very, very lean and skinny, right? That doesn't mean that they're very strong, that they're able to jump very high or be very, those kinds of things. So that we just kind of have to balance all of that out, if that makes sense. That's the idea of specificity. Okay.
Also, under like on the PowerPoint, I saw like the certain adaptations under the specificity slide. And I have a question on the velocity of movement as well. Sure.
All that really means is that if you want to get better at going fast, you need to train going fast. If you want to be a better sprinter, you have to sprint, right? If you want to make a muscle contract very quickly, then you have to make the muscle contract. You have to practice making it contract very quickly. Okay. So if your sport or your activity requires things where you move fast, which is pretty much everything, then you probably need to do some work on using a lighter weight, but going really, really fast. I don't know why you would bench press really fast. That's kind of dumb, but do knee extensions really quickly, or do plantar flexion really quickly, because that's part of, if you want to run or jump or something that has to happen with that. Okay? Okay. Excellent. All right. Well, do y'all feel like was that a reasonable review of what we were going to get on Friday in some ways? Okay. So let us do this. You know what? I'm going to go ahead and we'll do about 15 minutes of cardiovascular system stuff, and then we'll take our break, and we'll roll from there. So let me move where I have. Oh no, it's over here. Okay, perfect. So I've got two screens in my office. I got to make sure that I get this one where I want. And now I'm going to share the cardiovascular system slides. Okay. You guys can see all of this and you see the actual slides. You don't see the presenter view of it, right? Yes, no,
Yes.
maybe, yes. Okay, sweet. So we're going to move away from the neuromuscular system. We're going to move away from muscles, okay? And we're going to talk about the cardiovascular system and the pulmonary, or what some people refer to as the respiratory system, so kind of lungs, all right? And that's going to be our jumping off point into talking about more kind of endurance aerobic type training, all right? So again, like we did in the neuromuscular system, I'm not going to go point by point through every little structure, kind of all of the anatomy of the cardiovascular system. I'm going to hit a few high points, tell you guys what I want you to know, but I know you guys have seen much of this before. What we're really going to focus more of our time on is kind of the idea of the physiology of it, like how does it contract, and what is stroke volume and heart rate and cardiac output, and how are those things going to be regulated? Because when we exercise, those things are going to need to change in a certain way to let us exercise. And we need to understand kind of how all of that works, okay? So cardiovascular system is really important, okay? It actually plays a multitude of roles, some of which we don't even really realize. And Dr. Kellerwan gets mad at me when I say this, but in a lot of ways, the cardiovascular system is a support system. It does things that supports the function of muscles. It does things that supports metabolism. It does things that supports nervous system function, okay? And so those things can't work correctly if the cardiovascular system also isn't working correctly, all right? And so in a lot of ways, it is, you can argue that it's the most important kind of functional physiological system. It is certainly the system where we have the largest amount of changes that can occur both with training and with detraining, or with being sedentary and those kinds of things. So a lot of the deleterious changes that take place in conjunction with obesity and being sedentary are the things that cause cardiovascular disease and all of that. So we need to understand what sort of normal function is so that we can understand what pathological function is going to look like, okay? Muscles are the place where we generate force to be able to allow us to move, okay? But when we exercise, or we do a lot of things, when we play sports, we do something that's related to performance, we need to be able to contract muscles over and over and over again. It's not just kind of a one-off thing. And so in order to be able to contract muscles multiple times, we need to be able to generate lots of energy. We need to be able to clean out and get rid of metabolic byproducts. We need to be able to bring hormones and other things to those muscles, neurotransmitters to those muscles, in order to get it to continue to function the way that we want. And so the cardiovascular system plays a huge role in controlling exercise and performance, especially during almost anything that lasts more than about, say, 20 or 30 seconds, okay? Some people will say maybe 2 minutes or thereabouts, but I would argue that anything that really goes beyond about 20 seconds or thereabouts, we're gonna have to be able to change what's going on in the cardiovascular system, or we're not gonna be able to continue to exercise or perform at that particular rate, okay? So big key thing for exercise and performance. And because of that, when we do things where we exercise and we go for relatively long periods of time, you go for a run or you bike, or even if you do like step aerobics or things like that, we're going to see lots of adaptations in the cardiovascular system. We're going to see specific changes in the heart. We're going to see specific changes in conduit arteries. We're going to see changes in the number of capillaries that we have. We're going to see changes in where blood is going from one organ to the next and things. With these kind of chronic adaptations. And the vast majority of them are going to help us to be better at exercising and better at performance. We can run faster, we can run farther, and those kinds of things. And the good part of that is that the adaptations that help us with exercise are also going to help prevent cardiovascular disease. They're going to make things work better. The heart's going to work better. Your blood vessels are going to be bigger, and you're going to be able to deliver more blood in places. And those are going to be the things that are going to help us counteract cardiovascular disease. Okay, so we are mostly going to focus on these first two functions: delivery of oxygen and removal of carbon dioxide and waste products. That's mostly what we're going to cover in class. I'm sure you guys have talked about hormones and the transport of hormones, or actually endocrinology, those kinds of things in human phys. You'll talk a lot more about kind of the hormonal control of blood glucose and the regulation of temperature, and maybe a little bit even of exercise and immune system function. There are other things that are going to be kind of vital functions of the cardiovascular system when you take exercise phys with Dr. J or with Dr. Mike. We're really going to focus on these first two. Okay. We will talk about kind of the primary anatomical organs, the heart, which is in essence a pump. Okay. It has one job, and it is to contract and to move blood around in your body. We're going to talk about blood vessels, both arteries and arterioles and capillaries and venules and veins, which in their simplest form, they are channels or tubes through which blood is going to move. It's going to move it away from your heart, and we're going to use the blood vessels to get that blood to a certain tissue and then carry it back away from that tissue to get it back to the heart. And we'll talk about kind of how the heart functions and how the blood vessels can change and do some different things. And then what I think is maybe the most kind of underappreciated and under talked about component of the cardiovascular system is blood itself. Okay. And so blood is the fluid that is made up of water and red cells and white cells and platelets. That is going to be the thing that the heart pushes around. But the blood is the place where here is where the oxygen is. Here is where the nutrients are. It has the plasma that you use when you sweat to reduce your core body temperature. It's the place where the hormones are carried. It's the place where glucose and fat and other nutrients are carried. And so it's a really, really kind of key and maybe underappreciated component of the cardiovascular system. Okay, so we'll get into a little bit of the basics of some of those things. Here's the heart. Ours has 4 chambers. You are looking into a person's chest, and so everything is flipped around here. So what you see on the right is actually the left side of the heart, and what you see on the left is actually the right side of the heart. All right. All I want you guys to know, all I want you to know are the 4 chambers, okay? The left and right atria and the left and right ventricle. And I want you to know the most basic movement of blood, okay, through the chambers of the heart. That blood comes in from what I'm going to call systemic circulation. So venous blood in circulation that is coming back to the heart, returns through the superior vena cava into the right atria. It then goes into the right ventricle. It's then going to send it off to the lungs. It's going to return from the lungs into the left atria. It then gets moved into the left ventricle, and then it leaves out through the aorta with higher levels of oxygen back into systemic circulation. That's all you got to know. I don't care that you know what the name of the valves are. I don't care that you know what chordae tendineae are. I don't care that you know the names of these vessels or why, right? We have pulmonary arteries are one of the only arteries that have low oxygen content and those kinds of things. And the pulmonary veins have high oxygen content, which seems backwards, right? I don't care that you know any of those things. I just want you to know the chambers, and I want you to know how blood moves through there, because that's the stuff that we're going to talk about, okay? Very basic is it comes in from here, it has X amount of oxygen and CO2, it then goes to your lungs and some things happen, and it gets rid of its CO2 and it adds oxygen, and then it comes back. And then we really care about, when we talk about cardiovascular system function, at least in this class, we are mostly going to talk about what is happening when the left ventricle contracts. Okay? The left ventricle will contract and push a certain amount of blood out. It's going to contract a certain number of times per minute. And those two things are going to get us kind of our main exercise-related cardiovascular parameters, is what is happening here in the left ventricle. Okay?
So you want us to know the 4 chambers and how blood moves through the left and right atrium and the left and right ventricle?
That's correct, Nia. and probably the relative amount of oxygen and carbon dioxide in blood in each of the chambers. Okay, so right side, low O2, higher CO2, left side, lower CO2, higher O2. Okay, any other questions?
Can you repeat that real quick?
Yeah, sure. So the right side of the heart, so the right ventricle, the right atria, that's going to have blood that has come back from systemic circulation. So it's going to have relatively higher carbon dioxide levels and relatively lower oxygen levels. That blood then goes to the lungs where it's going to offload the CO2 and onload some oxygen. So when it gets back to the left side of the heart, it has relatively low amounts of CO2 and relatively higher amounts of oxygen.
Gotcha. Thank you.
Okay. Any other questions? Okay. Have I told y'all that I never had a class in anatomy? We talked about this? No? So to just show you guys how important anatomy class is, I've never had a class in anatomy in my entire life. I've taught anatomy and physiology. Never had a class in anatomy. Now I don't know shit about anatomy. I don't know anything, right? I just learned enough to make it useful for whatever it is that we do in my lab, and then I have to be able to teach in particular classes. But if you know a lot of, like, I know a lot of internal anatomy, to do a lot of physiology, you have to understand like the cells and the structures, like on kind of internal systems and those things. But I don't know anything about bones. I don't know anything about muscles and nerves. I don't know the names of any of those things. So a cautionary tale about how much of all of that you guys may or may not use in your future career. Okay. So there we go. We talked about cardiac muscle a little bit when we were doing the skeletal muscle stuff, but if you guys remember, cardiac muscle has striations, so it has this kind of very tight alignment of actin and myosin into sarcomeres and myofibrils and things, just like skeletal muscle does. It has sort of very few central nuclei. It has the nuclei are out near the periphery, just like in skeletal muscle. The thing that makes cardiac muscle different than skeletal muscle is the myocardium, or kind of collectively cardiac muscle in the heart, has a giant and extensive capillary network. You have a huge number of capillaries that are going to bring blood to the heart, okay, which is good. And then in skeletal muscle, even in people that are very highly aerobically trained, the mitochondria only occupy maybe 5 or 6% on the top end, maybe 8% if you're really well trained, of the cytoplasmic volume inside a muscle fiber. In cardiac muscle, it's almost half, okay? So basically, if you cut open a cardiac muscle cell, what you see on the inside is mitochondria. You see huge numbers of mitochondria. And so because of this, because you have all of these mitochondria, and because you have all of these capillaries to bring oxygen to those mitochondria, that's why your heart has been contracting since, I don't know when we first see heartbeats in a fetus. Is it like a month or 6 weeks or something like all of that?
It's about 6.
I'm sorry, Emma, is it about 6 weeks?
I think so.
Yeah, it's somewhere in there. I should, with the advocacy of all of these anti-abortion heart rate laws, I should probably know kind of where that is. But the take home is just like, imagine, right, like how old you are. Your heart has been beating for however old you are, plus, add another 6 months to all of that, and your heart's never gotten tired. It's for the most part going to continue beating, right, for maybe until you're 80 or 85 or 90 or 100 years old. Can you imagine how tired your bicep would be if you were just doing curls like this, and you've been doing curls for 21 years straight, okay? And so because it has all of these mitochondria, it has a very large capacity to use oxygen and do aerobic metabolism. And so it can generate lots of energy for actin and myosin to form cross bridges and break those cross bridges, without accumulating any metabolic byproducts and doing anaerobic metabolism, which is what will lead to fatigue. Okay. So we'll talk about when you have a heart attack, why that's a sign in some ways that these mitochondria are not getting enough oxygen, and why that produces certain symptoms a little bit later on in class. Okay. Cardiac muscle is going to have some very specific structures that skeletal muscle doesn't. One of them is called a desmosome. The other one is called a gap junction. These two things occur at a kind of collective structure called an intercalated disc. And what that looks like here is an H&E stain of cardiac muscle fibers. And so you see how they look nice and striped. This is what skeletal muscle would look like under a microscope. Here's a nucleus. Here's the individual kind of sarcomeres and myofibrils that are going to be there. The places where one fiber connects to the adjacent fiber, that's called an intercalated disc. And at that intercalated disc, if you see kind of, we're going to move ourselves over here into this cartoony version. At the intercalated disc, there are the desmosomes and the gap junctions. So desmosomes are, I don't know, they're like locks or something, kind of clamps. And what they do is they grab onto both sides, they grab onto the muscle fiber on either side, and they lock them down. And in doing that, they're going to hold them together very, very tightly. So cardiac muscle fibers are very tightly bound to the adjacent fibers. And then the other thing that happens is we are going to have these gap junctions here. And the gap junction is just a hole. That's really all that it is. It's just a pore or a hole. And it allows calcium and sodium and things, these ions, to pass back and forth. And that's going to help us to transmit action potentials from one cardiac muscle fiber to the adjacent cardiac muscle fiber by having these gap junctions that are going to be there. And so these are structures that skeletal muscle doesn't have. And they're going to play a little bit of a role in why cardiac muscle is able to contract or become excited and move action potentials along their length a little bit differently than skeletal muscle does. Okay. All right. It's 11:51. We'll go ahead and stop here. And okay, I'm back recording, and I'm back to screen sharing. So here we go. All right. So we've got those. Click one more time, and on we go. All right, so if we know a little bit about the structure of the heart, kind of what it looks like, the next really big thing is we need to appreciate how it is that the heart contracts. Because if its job is to move blood around and to do things, then we need to understand kind of how that contraction is going to start, how it's going to generate, how it's going to move around in the heart, because that's going to be one of the things. The frequency with which it contracts and the strength with which it contracts is one of the main things that changes during exercise. Okay, so cardiac muscle, much like skeletal muscle, is going to experience what we call a synchronous contraction. It's an all or none type of thing. So in general, if we've got normal function, if one part of cardiac muscle contracts, then the entirety or the rest of that cardiac muscle or the rest of the heart is also going to contract. Okay. The cells of cardiac muscle, unlike skeletal muscle, have something that we call an intrinsic rhythmicity. And what that means is that cardiac muscle cells have leaky sodium channels, and they will generate their own action potentials over time. Okay? And so if they don't receive a signal from, say, the SA node or the AV node or a Purkinje fiber or something, then the muscle itself will spontaneously depolarize. Although that's a little bit slower than other things. Okay, so they have this intrinsic rhythmicity, which makes them very unique and makes them different than skeletal muscle. Okay, so to get this to happen, they require no external stimulus. Okay. That's not the normal way that cardiac muscle contracts, though. The normal way, it doesn't require an external stimulus, but at least it's sensitive to an external stimulus, is through something called autoconduction that makes use of what we call the cardiac conduction system. And I'll talk about what those two things are in the next slide. Okay, so there's some nervous system innervation in cardiac muscle, and those things are going to fire, but then they're also going to be able for you to send some signals to the heart or through this autoconduction system to alter heart rate up and down, or to alter the strength of contraction up and down. With no influence whatsoever, which rarely ever happens, okay, the intrinsic rate of contraction of most people's cardiac muscle is about somewhere between maybe 70 and 75 beats per minute, okay? 70 to 75 beats per minute. That's the intrinsic firing rate. We'll talk about why most people are never at a heart rate of 72 beats per minute, because I can do fun things like, say, Savannah, we're about to have a pop quiz, and I can instantly make her heart rate go up by getting her to release epinephrine and norepinephrine. Or I could have Nia close her eyes, and we could do some deep breathing exercises for about a minute, and I would decrease epinephrine and norepinephrine and increase acetylcholine and increase her parasympathetic, and I can make her heart rate go down from some of those kinds of things. So we always are kind of at the mercy of the balance of our sympathetic and parasympathetic input into cardiac tissue, and most people are never at like zero on both of those, and so that's why we rarely have a heart rate that's about 72 beats per minute. Okay, Emma, you have a question?
Yeah, I was just wondering how, if at all, that's related to like people's resting heart rate.
So let me talk about the conduction system, okay? And then we'll talk a little bit about kind of how resting heart rate is regulated at the end of that, okay? Because once we get this, then that will hopefully make a little bit more sense, okay? So there are 4 components of the cardiac conduction system that I want you guys to know. So there are really 4 different nervous system. That's what they really are. They're nervous tissue structures that are contained in the heart that are going to play a very significant role in initiating a contraction in one part of the heart and then transmitting and moving that contraction in a very orderly manner kind of down the heart and, you know, from the atria down into the ventricle so that we can have normal cardiac function. So the pacemaker in the heart, or the place where the vast majority of all action potentials that cause the heart to contract originate, is called the SA node, or the sinoatrial node. It's located in the top of the right atrium. So most cardiac contractions, most heartbeats are initiated in the right atrium. Okay, so the right atrium, the SA node depolarizes, it generates an action potential that moves across the cardiac muscle fibers, across sort of this part of the ventricle until it reaches the AV node. It's also going to move across over into the left atria this way, okay, along the muscle fibers. But it's going to reach the AV node, which is located in the wall here between the right atria and the right ventricle. And the AV node is going to depolarize. It's going to then send an action potential down the septum of the heart through these nerve fibers that are here, that are basically like an axon, down these nerve fibers that are sometimes called the bundle of His. They are other times called the AV bundle. It's the same thing. It's just nerve fibers that run down the septum of the heart, and it's going to move this very quickly. So action potentials in this nervous tissue are going to move faster than action potentials moving along the surface of the cardiac muscle. So it's going to move it. We're going to quicken the speed down like this, okay? It's going to reach the bottom where they're going to turn and start to come back up, and then they're going to begin to branch off into these many smaller little kind of nerve fibers or little axon branches that we're going to call Purkinje fibers, okay? And the Purkinje fibers are going to kind of wrap themselves around the ventricle. And so having the AV bundle and having the Purkinje fibers are going to allow for very, very fast conduction of action potentials, and therefore it's going to let us initiate a contraction in the ventricles that's going to start at the bottom and quickly, almost instantaneously, but not quite, work its way from the bottom up, okay? And if you guys note, the sort of the pulmonary arteries and the aorta, blood is going to leave the heart going up. It's going to leave it going up against gravity. And so what we need is, we need the heart to begin contracting at the bottom. The bottom contracts and it pushes blood up. And the next piece contracts and it pushes blood up farther, and so on, like we're working toothpaste out of a tube or something, okay? And so that's going to push blood from the bottom up and help get it out by doing all of that stuff, okay? And so that's the utility of having the cardiac conduction system. Now, the SA node, and in some instances the AV node, and then the aorta and the ventricles, these structures are going to have receptors that we're not going to talk about at all for some neurotransmitters. They're going to have receptors for epinephrine and norepinephrine, which are going to come from the sympathetic nervous system, and they're going to have receptors for acetylcholine, which are going to come from the parasympathetic nervous system. And the SA node has things from both, and then mostly the ventricles are going to have innervation from just the sympathetic nervous system. But the idea behind all of this is, all of us and our heart rate at any moment in time, okay, is going to reflect the net balance of sympathetic and parasympathetic nervous system input to, we'll just make it very simple and say the SA node. It's not always just the SA node, but that's the general thing, okay? And so when you are resting, if you are calmer, you're going to have very low sympathetic nervous system activity, and you may have a little bit to a lot of parasympathetic nervous system activity. And so to bring your heart rate down, there's some midpoint, as we talked about, right, that was about 72 or ish beats per minute, which is kind of the inflection point. If we remove all of the sympathetic nervous system input, that'll bring us down to about 72 beats per minute. If we then begin giving parasympathetic input, then it's going to lower it farther from 72 down to 70 or 60 or 50, or it can get all the way down into the high 20s or the 30s if you're really relaxed and you're very, very highly trained, okay? And then when we want it to go back up, we can remove the parasympathetic, and as we remove it, that drives us back up towards about 70 or 72, and then we can start adding sympathetic on top of all of that, and it will drive it up even higher, okay? So your resting heart rate, or really your heart rate at any moment in time, is the net balance between sympathetic and parasympathetic input to the cardiac muscle. Okay. So Emma, does that answer your question a little bit?
Yeah, it does.
Okay, perfect. All right. And so we'll talk about what happens during exercise. Your heart rate goes up. So there's some very predictable changes in input that are going to happen during exercise. When you chronically train using aerobic exercise, your resting heart rate's going to fall. And so that's going to lead to some very predictable changes in sympathetic and parasympathetic input and stuff as well, okay? Okay, so if that's how we initiate a heartbeat, then a single heartbeat we often refer to as one cardiac cycle, okay? One cardiac cycle. So within one heartbeat, within one cardiac cycle, we're going to break down what is happening in the atria and the ventricles into two distinct processes or time periods, if you will, okay? And we're going to call those systole and diastole. Systole is when, or the period of time or the event where that particular chamber is actively contracting, and diastole is the period of time when, or the event when, that particular chamber of the heart is not contracting, when it's relaxed And when it's relaxed, it's going to fill with blood. So during systole, when that chamber contracts, it's going to move the blood out of it. And then during diastole, it's going to fill back up with blood. Okay? All chambers undergo these alternating periods of systole and diastole during each cardiac cycle. So when you have one heartbeat, you're going to have both atria are going to initially be in diastole. They're filling up with blood. Then they're going to switch from diastole to systole. They're going to contract. While the atria are in systole, the ventricles need to be in diastole so that they're relaxed, so that blood will then move from the atria down into the ventricles. Then the atria relax, and then the ventricles contract. The ventricles go into systole. So when the ventricles contract, they're going to eject blood out either to the lungs or into the aorta, and then blood is going to come back into either from the pulmonary veins or from the vena cava into the right and the left atria. So in a typical person with a resting heart rate of, say, 70 beats per minute, about 60% of a cardiac cycle is going to be spent in diastole, compared to about 40% being spent in systole. As your heart rate decreases, the amount of time spent in diastole increases and the amount of time spent in systole decreases. When your heart rate goes up, like it will during exercise, then the amount of time in diastole is going to get smaller and the amount of time spent contracting is going to go up. And there are some consequences of that as we reach very near to our age-predicted max heart rate, that we'll spend so little time in diastole that may become a limiting factor in how much blood we can get into and then therefore get out of the heart in a given period of time. Okay. If you've got a resting heart rate of a heart rate of about 75 beats per minute, then that means every heartbeat takes about 0.8 of a second to occur. So if you wanted to, then you could take your 0.8 of a second, multiply that by 6, right? So you've got about somewhere between 0.45 and about 0.50, half a second-ish that's being spent in diastole, and then about 1/3 of a second or thereabouts that's being spent in systole at rest, okay? Not that those numbers really mean anything. I just kind of want you guys to appreciate that there are these alternating cycles of this, and as heart rate becomes manipulated by either going up or down, then those things are going to change. And that can have some consequences on our ability to exercise. It can have some consequences on blood pressure and things as well. Okay. Nobody freak out, but I'm going to show you guys a picture of what's called an electrocardiogram, an ECG or an EKG. An electrocardiogram is just a measure. It's basically a chart that shows the electrical activity that's happening in your heart. If you guys take exercise testing and prescription, you will learn in there like where and how to attach all of the electrodes to do an electrocardiogram. You can do it with as few as 3 electrodes or 3 leads on there. The kind of industry standard is to do what's called a 12-lead EKG, and you put electrodes all around your heart. You put some over here, you put some on your back, you put some up on your shoulders. And what we're basically doing is, by doing that, we're getting, in some ways, this sort of 3-dimensional picture of where the electrical signals are and what they're doing across the atria and the ventricles, kind of up and down and left and right in the heart by having different electrode locations. Okay, so I'm sure you guys have seen this before. I'm not going to have you do very much with this other than maybe be familiar with what a normal one is going to look like. But when we see here, basically the tip of what's called an R wave to the next R wave, this is going to represent sort of one cardiac cycle or one heartbeat. I like to look at it as from one P wave to the next P wave. That's also going to be kind of one cardiac cycle. But what we have is when the atria depolarize, so the SA node fires and the atrial cardiac muscle is going to depolarize, we're going to get a change in membrane potential which gets picked up. That's this P wave here. Okay, That's the P wave. So that's the electrical signal moving through and causing the atria to contract. And then in some predictable time manner following that, we're going to go through the AV node, down the AV bundle, into the Purkinje fibers, and we're going to get this contraction of depolarization in the ventricles. And that's going to look like this next wave, which we call a QRS complex. Please don't ask me why it spikes the way that it does or those kinds of things. It's really, really, really beyond the scope of our class. Just know that this QRX complex denotes ventricular depolarization. And somewhere hidden in all of this would be a change in membrane potential that would denote that the atria are actually repolarizing. So we then, at the end of all of this, ventricle depolarization has happened. We're about to enter into ventricular diastole. And so then it stops contracting. We come out here and we get what's called a T wave, which is going to follow after this. This is denoting a repolarization of the ventricular cardiac muscle. Okay, and so now once that has depolarized or repolarized, then it can contract again. And so what you get are these cycles of P, QRS, T, P, QRS, T. And if we measure the distance between these two things, each one of these little squares on an EKG represents an amount of time. And so we can count the number of R waves that we see over a certain amount of time, derive that into 60 seconds, and you can determine heart rate. Okay? And so theoretically, we should have a P wave that precedes every QRS complex and a T wave that follows after all of these if we have normal, proper cardiac function. We don't always have normal, proper cardiac function. Excuse me. If you take chronic disease class, you'll have to learn what a bunch of arrhythmias look like and kind of what, when you have certain kinds of cardiovascular disease, kind of how that might change what your EKG looks like. But for our class, all I want you to know is that there may be some changes from this S to the beginning of the T segment in people that have had a heart attack or people that are experiencing blockages of blood flow to their cardiac muscle tissues. There's these noticeable and predictable changes that are going to occur in ventricular repolarization. There's a thing that's called S to T segment depression, where it doesn't jump back up like this quickly. It sort of stays down, and then it sort of stays down here, and then the T wave gets initiated, if it gets initiated. And that's a sign that you're having ischemia or a lack of oxygen to some parts of the cardiac muscle tissue. So it can be very predictive of people that have certain kinds of cardiovascular disease. Okay. I think I have mentioned to you guys, maybe I haven't, but if this kind of stuff is interesting to you, you don't have to be a cardiologist. There's some really, really good jobs, well-paying jobs if you like working, especially with older adults, that I try to tell people about. It's called cardiac rehabilitation. Almost every hospital now has a cardiac rehabilitation unit. And what they do is they take people that have had a heart attack or had some kind of revascularization. They've had a stent put in or they've had bypass surgery, which usually happens after you've had a heart attack. And they do exercise training on them. And they do it in the hospital where they can monitor them. And one of the ways that they monitor them is they have them walk or jog or ride a bike or do some things while they have these EKGs on. And so if you can get good at reading these to be able to identify if there are problems, then you work in cardiac rehabilitation and you're the person that monitors them during exercise. You're the person that prescribes them exercise based upon the FIT principle and the overload principle and those kinds of things. Cardiac rehabilitation has become the standard of care, which means that insurance companies will reimburse for it for people that are post-heart attack, because having 8 to 12 to 16 weeks of cardiac rehabilitation dramatically improves the survivability and decreases the risk of having either death or another heart attack in people that have already had one. You can get a job in cardiac rehabilitation just with a bachelor's degree in exercise science. Okay? There are programs that are master's degrees. They're usually called clinical master's degrees in cardiac rehabilitation where you learn all about all of these things and kind of how we prescribe exercise in special ways for these particular populations. Like Texas A&M has a program. I think there's some other places that do. But these are jobs that pay, you know, depending, that pay a lot of times like physical therapy jobs or occupational therapy jobs or things like that. You don't necessarily have to go to more school to be able to get them. Okay. This is just showing electrical events and their kind of thing that's going to be there. All right, so what I want to do now is we're going to talk for the rest of today about a few kind of very key, this is more what I would call a physiology thing. So kind of the cardiac conduction system, that's anatomy, but what it really gets at is function, okay? And so when the heart beats, when the heart is going to move blood, we need to concern ourselves with three distinct variables, okay? One of them is called stroke volume. One we've already talked about in passing, and that's heart rate. And then the other one is called cardiac output. Cardiac output is the product of stroke volume and heart rate. So you take your stroke volume and you multiply it by your heart rate, and that gets you a cardiac output, okay? So we're going to start off with what stroke volume is. Please don't get this twisted and confused around with what cardiac output is. Stroke volume is the amount of blood. So it's a volume, a fluid volume. It's the amount of blood that gets pumped out of the left ventricle every time the left ventricle contracts, okay? So the ventricle squeezes and it contracts on itself and it ejects some blood out into the aorta. If we were to run, say, a catheter into your femoral artery, which people will do, and we snake it all the way up until it's sitting in your aorta, which people can do, and we put a little flow meter in there, we can measure how much blood is leaving the left ventricle every time it contracts. In a normal kind of average college-aged person, stroke volume is going to be somewhere around about 80 milliliters of blood, okay? About 80 milliliters of blood per heartbeat when you are at rest. So I'm holding up this thing that I have here in my office. This is a thing of hand sanitizer that they gave us. This bottle is, you know, maybe 5.5 or so inches tall, and it's about 2 inches around. This bottle will hold 240 milliliters of fluid. So you can imagine then that every time your heart beats at rest, if I'm an average person, I'm ejecting, you know, about from there to the bottom. So about a quarter of what this is every time your heart beats, okay? So we can calculate stroke volume in a way that is a little, I think, confusing, but I'm going to try to give it to you guys in kind of as straightforward a manner as I possibly can. So people will say that if you want to figure out the amount of blood that leaves the heart every time it beats, we need to know two things, okay? We need to know, first, the amount of blood that was in the left ventricle, okay, before it began to contract. This is termed end diastolic volume, or EDV. End diastolic volume is the total amount of blood in the left ventricle at the instant it transitions from diastole into systole. So at the end of ventricular filling in the left ventricle, the total amount of blood that is in there, okay, that's end diastolic volume. Then the heart contracts, and it's going to eject some amount of blood. Under a lot of circumstances, under resting conditions, okay, when the heart is finished contracting, there is still going to be some blood that is left in the left ventricle. It does not eject all of the blood that is in there. So if we know how much was in there when it began contracting, and we know how much is in there at the end of the contracting, so the end systolic volume, if we subtract those two things from each other, that tells us then how much was ejected out. So I have an end diastolic volume, let's just say, of 100, and I have an end systolic volume of 20 milliliters, then that would give me a stroke volume of about 80. Okay? And so another really clinically meaningful parameter in all of this is something called ejection fraction. Okay? And so ejection fraction is a way to express the percentage of end diastolic volume that is pumped out at rest. Okay? And so what it is basically is stroke volume as a percentage of end diastolic volume. And so a normal person at rest, their ejection fraction is about 2/3. It's about 67%. Okay, somewhere between 60 and 70%. Okay. People that have certain kinds of cardiovascular disease, where they have weak contractions of the left ventricle, have a much smaller ejection fraction. Maybe their ejection fraction is 50%, okay, of end diastolic volume, or 40% of end diastolic volume. Other times it's not just a weak ventricular contraction, but maybe people that have high aortic blood pressure. So you're very hypertensive. The pressure that you have to exert by the ventricle to overcome the pressure in the aorta is very high. And so there's lots of pressure preventing it from going out. And so that may drive your ejection fraction down. As your ejection fraction falls, then you're getting less blood into circulation, and that can have some really kind of deleterious effects on things. So ejection fraction percentage can be indicative of cardiovascular disease. It can be indicative of poor heart function, as well as sort of hypertension and high blood pressure. Okay, so this is a thing that we can oftentimes calculate. Now, in most people, rather than running a catheter in, to sort of run a central line into your aorta and try to measure it directly, what people will do is something called, they'll put a Doppler ultrasound on, okay? And they'll get what's called an echocardiogram. And they put the ultrasound on, and they visualize your heart much like they would visualize, say, a baby in her mom's uterus, okay? But you can do that, and then you can also measure blood velocities and things from, like, of the aorta and things from that. And so you can put the ultrasound on, and you can measure the diameter of the aorta, you can measure the speed of blood moving through the aorta, and from those two things you can calculate a volume. And so we can figure out, like, what is stroke volume, and then we can guesstimate based upon the three-dimensional structure what we think their ventricular size is, so we can guess it in diastolic volume. We can try to calculate ejection fraction. So there's some really kind of interesting and cool things that we can do with all of this, but I show you guys all of this to try to demonstrate that stroke volume is really important during exercise, okay? But it's also really important as a clinical diagnostic tool for people that have cardiovascular disease. So any of you that want to be doctors or PAs or things, you will need to look at a person's ejection fraction to kind of understand what their cardiac system is doing. Okay. All right. So we talked about heart rate to some extent already in its regulation. So a heart rate is just like the beat. When you take these stroke volumes, so you take the amount of blood that leaves the heart every time it contracts and it beats, and then you take the number of beats that you get in a minute, and you multiply those two things together, we get a number. Okay, we get a volume of blood that is going to be pumped out of the left ventricle per minute. So if we put a stopwatch on and we said go, and we timed you for a minute, we counted up the number of heartbeats that you had in a minute, and we know how much blood leaves every time, we can get what we call your cardiac output. Okay, your cardiac output. Strangely, cardiac output is abbreviated by the letter Q. Okay, so you will hear me refer to it kind of interchangeably as Q or cardiac output. And so the general units of cardiac output are going to be liters of blood that are going to be pumped out of the left ventricle per minute. Okay, in kind of a normal size college students, in women, Normal cardiac output is about maybe 4 or 5 liters per minute at rest. And then in a normal college-sized guy, it's maybe 5 to 7 liters per minute at rest, okay? So imagine, right, that you have these 2-liter bottles of blood, and you're a college-age woman and you've got 4 of them, and you're a college-age guy and you've got 5 or 6 of them. That's how much blood is moving out and kind of through your heart and then back out into circulation every minute, okay? We don't talk about it here. We do it a little bit later, but interestingly enough, blood volume, most women college-age women have about 4 to 5 liters of blood in their body, and guys are somewhere around 5 to 6 or 7 liters of blood in their body. So we typically will say that at rest, cardiac output is pretty close to equal to the entirety of your blood volume. So you're going to move all the blood in your body through your heart like once, basically, every minute at rest. As we exercise, both our heart rate and our stroke volume are going to increase. And so if those two things go up, then obviously cardiac output has to go up. And so in a regular person, cardiac output is going to go up from maybe 4 or 5 liters per minute to maybe 20. So it's going to go up maybe 5 times or thereabouts. In really, really elite athletes, and we'll talk about why they have larger stroke volumes, which is the main thing that drives this big increase. They may be able to get all the way up to, say, 35-ish liters per minute in elite athletes. And this difference between these two things in kind of the high end, the fact that an elite athlete can move almost twice as much blood through their heart and out to their tissues during maximal exercise is one of the reasons that they're so much better as athletes. This is going to have a really, really big effect. Okay. I want to talk really briefly about blood pressure because it's one of our markers of cardiovascular disease, and it's one of the most common types of cardiovascular disease is an elevated blood pressure. So I want us to understand a little bit about what it is and kind of how we go about measuring it. So blood pressure is a measure of the pressure that is exerted by the blood, the amount the blood is pressing on the wall, the inner wall of a particular blood vessel, okay? So we usually measure blood pressure in arteries. We could try to measure it in a vein, although it's so low that it's really hard to get it. But we typically measure it in an artery. And in theory, we can get a blood pressure in pretty much any superficial artery in your body, okay? Most commonly, we measure it in the brachial artery here, kind of run under your bicep, okay? Never had anatomy, y'all gotta be impressed by that, both brachial artery location and bicep, right? I know those two things. I don't know much more than that, but I know that. It's going to be here, but we can measure it in your femoral artery, or we could measure it in, like your radial artery down here in your forearm or something. The technique for doing it would be relatively similar. But most of the things are done for brachial, okay? And as you guys will see then, we can extrapolate from the brachial artery pressure as to maybe what's happening with aortic pressure. It would be a little bit higher because it's closer to the heart, and then kind of what our ventricular pressures during contraction are very likely to be because they're going to be even higher still, okay? Usually when we're talking about arterial pressure, we express it as 2 numbers, okay? You're going to have a measure of what we call systolic blood pressure and diastolic blood pressure. And so systolic pressure is going to denote the highest pressure that we tend to see. And this is the pressure that is going to be exerted while the heart or the left ventricle is actively contracting, okay? The ventricle contracts, it's going to force blood out, which is going to raise then the pressure. As more blood comes out, it raises the pressure along the arterial chain. And so as it goes up, we can measure this particular increase. Diastolic pressure is the lowest pressure. And this is the pressure when the left ventricle is not contracted. So the left ventricle is in diastole. So the left ventricle is filling. So this is in some ways almost like resting blood pressure, right? The heart is not actively contracting. Like, what is the pressure in your arteries that needs to be overcome to allow blood to begin to move, okay? So systolic is the highest during active contraction. Diastolic is the lowest when we're filling, okay? I'm sure in one of the other classes, you maybe either already tried to take blood pressure in people. We don't do it in lab in this particular class. But if you're curious about kind of when you listen for blood pressure, like what are those sounds and what do they mean and what are we listening for and how do we pick what's what to get our numbers, I'd be happy to chat with you about that outside of class, okay? Another measure you may encounter, although it's less used these days than it was previously, is something called mean arterial pressure, or MAP, okay? And mean arterial pressure is a calculation. It's a way to try to characterize over the course of one cardiac cycle, let's just say, so a period of systole and diastole, it's a way to try to characterize the average, quote unquote, amount of pressure that's being exerted by blood on the vessel wall during a single cardiac cycle. And so what that does is, in general, we get this at rest, and so we calculate it by taking diastolic pressure twice and systolic pressure once. That's not the calculation that is here, but this will derive back into that. But it's basically 1/3 systolic pressure and 2/3 diastolic pressure. And that gives us, and that's because we spend 2/3 of the time at rest in diastole and 1/3 of the time in systole. And so we can see what's happening with mean arterial pressure. So when we exercise, systolic pressure tends to increase, diastolic pressure better not ever increase. If diastolic pressure begins to increase, we got to go to the hospital immediately. So as mean arterial pressure also increases with exercise, it's solely due generally to these increases in systolic pressure. And so people used to use this as a way to try to characterize, we're getting more information from this than just simply by what is your systolic pressure. I don't really know what they're teaching in medical schools now, but at least in the exercise community, the use of mean arterial pressure has kind of fallen out of favor in that particular way. But at least you guys have seen it, so if you ever come across it again, you've got something to potentially come back to. All right. So you may be asking yourself, all of this is great, Dr. Black. Why do I give a shit about cardiac output and heart rate and stroke volume, and really why do I care about blood pressure? Like what's the importance of all of these things, okay? And so I'm going to start with blood pressure. Here's why blood pressure is really, really, really important, okay? Blood moves in your body down a pressure gradient, okay? So the thing that allows your blood to move from your heart out to your tissues and then from your tissues back to your heart is very simply a difference in pressure as it moves along and through the blood vessels, okay? So we need to create a situation where we have the highest possible pressure in the left ventricle, okay? And then we need pressure to decline as we move out the aorta, down into our kind of large conduit arteries. We're taking blood away into our brachial arteries, into our femoral arteries, down into the popliteal and those kinds of things. As we move blood away from the heart, pressure is going to fall a little bit. As it moves out into arterioles, it's going to fall further. As it moves into capillaries, it's going to fall even further. And then as it gets out of the capillaries to get it back into the veins and the venules and then the veins and then back to the right atrium, we need this decline in pressure or the blood won't move, okay? Or the blood won't move. So you imagine this scenario. I do something and I make your aortic pressure go way up. So I put something in here, like I block off some of the stuff in your aorta and it makes your aortic blood pressure go way, way up. If your left ventricle then can't contract forcefully enough to raise the pressure inside the ventricle to be able to exceed aortic pressure, blood's not going to leave the heart, okay? And there's a clinical condition called congestive heart failure where something just like this happens, okay? There may be situations where your right ventricle can't contract forcefully enough to be able to move blood out over to the lungs, right? And so you're going to get stuff that backs up on the venous side. It's called venous congestion. That can be a problem, okay? Or there may be a situation where when things can't get out of the left ventricle, then it begins to back up into your lungs, and you're going to get swelling and pressure in your lungs. And so you're going to get pulmonary congestion. So blood has to move down these gradients, okay? So if things happen that change these gradients, we're getting pressure outside of the heart that is too high, or we're getting pressure in the heart that's too low, okay, then blood's not going to move in the way that it's normally supposed to. Or I put a thing on, I put a blood pressure cuff on your arm, and because the pressure inside your veins and your venules is so low, I can very easily smush those things and blood can't get back through them. So I can't get blood into them and I can't get blood out of them. So in those scenarios, then we're going to have impairments in blood flow, okay? And so this is why understanding blood pressure and knowing a person's blood pressure and knowing what happens to their pressure during exercise, when they lose blood and it goes down, they have blood loss, or when they have cardiovascular disease and they become hypertensive, why understanding what it is and knowing how blood moves is so unbelievably important, okay? Because if the pressure gradients aren't correct, then blood doesn't go anywhere, and that has consequences. And if you can't get oxygen to certain cells, those cells will die. That tissue will die. That tissue will not function correctly. You'll get tingling, you'll get numbness in nerves, you'll get inability to contract in skeletal muscle, right? You'll get lack of blood flow to the brain, and you can get neuron death and memory loss and all of these other kinds of things. So that's why blood pressure is so important, okay? All right. Questions about that? All right, well, this feels like as logical as any other place for me to call a stop for today, okay? We're about to transition into talking about blood, and so we'll pick up talking about blood tomorrow, all right? And we'll hopefully be able to get our way through the rest of the system tomorrow. So your test is going to be given to you on Thursday, and I'm going to want it back from you on Thursday. The test will be open book, open note, open Google, whatever you're going to manage to be able to do, okay? Because even if I tell you guys not to do it, some of you will not do it and others of you might, and I want it to be a sort of a fair playing field for everyone. As a consequence of all of that, though, what I'm going to probably do is either post the exam on Canvas, or I can email it to you directly. And from the time that I post it, you're going to have 4 hours, or that I email it to you, you will have 4 hours to complete the test and turn it back into me on Canvas, okay, or via email. For those of you that have other classes, for those of you that have work after class or in the evening or something else, I realize that this condensed time frame may create a little bit of a time issue for you. And so what I'm happy to do is to try to work with you, and you can email me and let me know, like, hey, Dr. Black, I have another class. My plan is to be Thursday, class is over. I'll post the thing when it's over, so you get it at 1, and then it's due at 5. That's my general starting place, okay? But if you email me and say, Dr. Black, I have another class after your class, or I have to work after your class, and I can't get to the test until 5 or 6 or 8 o'clock at night or something like that, then I will email it to you, and you'll get a certain amount of time from that point going forward to go to get it done. Or if you want it before class, you're like, I can't do it before class, but I'm going to get up at 6, or I don't really care, I can do it all in 2 hours, get it to me at 8:30, we can make arrangements like all of that, okay? I realize that, you know, your schedules are going to be, you know, maybe a little bit of an issue, and I'm happy to work with you, okay? Nia and Emma, I saw that y'all ask questions. Let me do one more thing. So the test is going to be multiple choice and kind of short answer essay-like things. For the multiple choice, I have created an Excel spreadsheet, and it's going to have like the question number, and it's going to have another column where you're going to type in what you think the correct answer is. going to email me or you're going to put on Canvas, you're going to send me back that Excel sheet that has your answers in it. Okay. And then you're going to send me as well your answers to the short answer questions, like typed out or written out, however you want to do that. Okay. That's going to help me. I have a program in Excel that I just copy and paste them in, and it tells me which ones you got right and which ones you got wrong, and I can grade very quickly by doing all of that. Okay, and that will help me get test grades turned around hopefully by the end of the day on Friday for everyone. All right. So Emma, I saw your hand first. You can ask your question, and then Mia, we can do your question.
You answered it. I was just gonna ask like when you were planning on posting it. So.
Okay. Cool. Nia?
How many questions will it be? Because I know you said you're giving us 4 hours to do it.
So there's about 50-ish multiple choice questions. And then there will be, I don't know, 5 or 6 or maybe probably no more than 7 or 8 kind of short answer questions. In a regular semester, when people come in and take it, most people finish in under an hour pretty easily. And so I feel like that 4 hours should be sufficient for you to like go through it and even be able to try to, on things where you're having some questions, like try to actually look for the answer. If you want, there may not be enough time to like do a real deep dive kind of research. I'm trying to pick a time frame where it will hopefully encourage rather than force, but encourage all of you to kind of fill out the study guide and look through the slides and maybe study a little bit and not just kind of leave everything right to the very, very end in that way, but also not give you such a short amount of time that you don't have a chance to kind of look at anything.
Okay.
Although that had occurred to me, like, look, you get an hour and a half and that's it, or you get 2 hours and we're done. Or all of you have to get on Zoom on your phone and point your phone at yourself at your laptop, so I can see your laptop screen, and we'll just sit here during class and all of you guys will be taking the test while I look over your shoulder to make sure you're not like using your notes and things. During the regular semester, that's how people that had to have a makeup or for some reason couldn't make the regular classroom, that's how I had them take their tests so that I can monitor them. Because the people in class need to use their notes, and so that's kind of how we did those things. But it's the summer. I'm more sanguine about that.
Okay.
All right. Any other questions?
I have one. I might have missed it, but did you say that for the short answer, we're also entering our answers in the Excel sheet that you're saying?
You can do that if you want. Like, I mean, you can type things into Excel and just into one cell and it just kind of strings them along. That will be fine. Or you can put them in a Word doc or something as well. It doesn't really matter. What I will probably have you guys do is email me the Excel spreadsheet and then load a Word doc or a PDF or a Google Sheet or whatever onto Canvas for the short answer portion. Because if we turn the Excel thing in, it's going to tell every one of you that you're like 90% copying off of everybody else, because hopefully you guys will all do well and you'll all have like the same answers, and so it will think that you copied. So
perfect. Thank you.
Lab 1 is due tomorrow by 11:59 p.m. I posted the data to make the graphs and things. It should be on Canvas. Try to make the Excel graphs or the Google Sheet graphs. Look for some YouTube videos if you're having trouble. If all of that fails, then holler at me this afternoon or this evening, and we'll try to get you squared away, or holler at me tomorrow after class in that way. If any of you did not turn in your resistance training critique yesterday, okay, Canvas is closed. If you want to email it to me now, I will be happy to take it, but I'll knock you a letter grade for not having it turned in until today. Tomorrow you can turn it in and I'll knock you 2 letter grades from whatever you actually earned in that way. I'm gonna try to get to work on grading those this afternoon so that you guys can and I gotta stay up on grading 1 so you guys can see how you're doing, but 2, it's gonna all start piling up, and then that will not be good for me. So I'm gonna try to get those graded this afternoon and get you guys stuff posted, okay? So that's where we are. Any other problems or concerns or things that I need to be aware of? Otherwise, I will see you guys tomorrow morning. Okay?
I just wanted to go ahead and talk to you about when I'll be gone.
Okay, yeah, that's fine, Savannah. We can. I'm happy to hang on. Let me stop sharing. Let me